Hello everyone, welcome to the video. So today we have a distinguished guest with us, Dr. Apratim Chatterji of IISER Pune, the Indian Institute of Science, Education and Research Pune. So he is a physicist and he currently works on biological physics, and he uses physics principles to understand complex systems and biological systems, and we'll be hearing a lot of interesting stuff from him today in this interview. So first of all, thank you so much, sir, for agreeing to be interviewed and for giving us some of your valuable time.
Yeah, so thank you, Arpon. It's my pleasure. I like talking to students. As you have seen, since I gave my lecture in St. Xavier's, then we had a long interaction. And I'm very happy to be here. It's a pleasure talking to students and taking ideas of research to
Thank you,
some of my
sir.
colleges. And
So I came to know of Dr. Chatterjee and his work because he came to our college. He visited St. Xavier's Kolkata to give a talk, and that was one of the I have attended a lot of conferences and talks in my undergraduate years, but this was probably one of the talks that had the greatest influence on me because for the first time I started seriously thinking about the physics of life, and the way he presented his work using the visuals and schematics, that was really very not only interesting but also very much digestible, because usually in a 1 hour or 2 hour talks it's very difficult to make students understand, but he did a very good job of it. So first of all, my first question to sir would be what is the physics of life for somebody who has no idea, and why suddenly this interest in the physics of life, and usually people have an idea that physics and biology are like vastly different subjects. So how did you come to this field, and what is your experience so far?
Thank you for asking this question. Actually, I have myself heard the term physics of life only 3, 4 years ago, most probably. And throughout, I mean, after class 10, when I promptly dropped biology, I have not been working on biological or biology related systems at all. So it is quite a surprise for me. It was a very surprise for me till the last 3, 4 years that I've started looking at living systems. But right now I'm enjoying it a lot actually. So let me tell you how I landed up in physics of life. What does this mean? Is it different from biophysics? Because biophysics is a term we have been hearing for some time. So for that, let me give you a background of what my career path has been or my educational path has been. So I am a student of Presidency College and I did my PhD in IISc. I was in PhD. I did my work on statistical physics, phase diagrams, phase transitions, completely as non-living as it can get, right? Yeah, so basically polymers, dead objects, and so on. And so my PhD was in statistical physics, and when I went for postdoc, I went into something called soft matter. So what is soft matter? It's essentially the physics or the statistical physics of large macromolecules, Brownian particles, polymers, interacting particles, and so basically it is applied statmech. Okay, so applied StatMech where large number of particles, molecules, macromolecules interacting by screen Coulomb interactions, where thermal fluctuations, Brownian motion is very important, and they interact and form different structures, or they show large response. Like steel is very hard, right? But on the other hand, some other material like rubber, you can easily pull it. So soft matter are those materials which show large response, small force, human forces, and you can easily stretch a rubber band. Steel you can't. So basically, soft matter is the system of such materials which show large deformation, and there often entropic forces are under play. And I essentially am interested in self-assembly, self-organization, and such stuff, and that's what I was doing till 2017-18, when I was suddenly pushed by my friends against my wish to look at chromosome systems. I said, I don't know any biology and I've never wanted to do much biology. Why do you want me to do it? I mean, there are so many biologists, chemists who are already looking at it. Well, no. We really want people who are using principles of physics or polymer physics as different from polymer chemistry to look at this problem, because if you are put in all the chemical details and the biological details, then you can't get the big picture. Whereas we want you as a physicist to give a different perspective and a big picture approach to some questions, whatever be there. So that's what I was doing. So and I was not very convinced. There was a PhD student. I said, okay, do something. If nothing comes out, I don't know any biology. Nothing I knew. Uh, doesn't happen. We'll leave and do our standard self-assembly, self-organization, soft matter, statistical physics stuff. But after 2 3 years, after I learned a bit, I just saw such a amazing, bewildering uh, range of phenomena, emergent phenomena, particles coming together and showing something. And I mean, biology might be living, but I am a physicist and I've been looking at chromosome. That's a dead molecule, right? I mean, there's nothing living about it. Cell, it's inside a living cell, true. But and there's so much strange phenomena which was there to explore. So why have a bias? Why don't I go just because it's living and I had my stupid school biases against biology. But here I'm looking at interacting molecules, which is the realm of physics, and how emergent phenomena comes about, right? I mean, just to get it clear. So I'm looking at chromosomes as dead molecules, but these large number of molecules inside the cell, they come together, they interact in predictable ways using random forces. There are Brownian forces at play, but somehow they interact and large number of them interact, and somehow you get a living cell. We all agree that a cell is living. We all also agree that the constituents are non-living. And so how do non-living molecules come together, interact, form emergent structures, cell membranes, whatever they do, the proteins, whatever they do, and at the end you get something living. There's a missing link, and I and nobody else in the world knows. And I'm very curious to figure out this missing link. It's not that I'll be able to figure out in my life, but I can take some small steps towards trying to investigate these questions, and maybe the next generation or the generation after next can figure out. So how do dead molecules come together using random stochastic forces, self-assemble, self-organize to produce a living cell? And this is a fascinating fundamental question which I'm very interested to know. Unfortunately, I'll die before knowing the answer, but that's okay.
Thank you
Yeah,
so
I mean,
much.
I don't know. I hope.
Thank you so much for the answer,
Yeah.
sir. So, it's definitely very interesting, and you talked a lot about self-organization and self-assembly. So, yeah, if you think about it, this entire human body is such a complicated structure. It's ultimately all made up of particles that follow the laws of physics. So, what makes them assemble in such a complex way that we are able to maintain a more or less normal and stable life for maybe 75 or 80 years? I mean, I was just having a discussion with one of my friend, and we were like, actually, if you think about it, humans, it's a surprise that we don't fall sick more often, because the body always have this
Absolutely.
ha-
Absolutely.
have this nature that if something goes wrong, then something else will take care of it, and this overall it maintains a self-sustained structure. So my next question would be, could you tell us in very like basic terms about self organization and self assembly in complex systems? What is that, and how does it happen, maybe with some examples?
Oh, okay. Yeah, yeah, sorry. Yeah, yeah. I use those terms, but yeah. So let me try to explain. It will take me 5 minutes. You have to bear with me because I suddenly can't throw self. Basically, what is the idea of self-assembly and self-organization at the global level? Before giving concrete examples, you know, uh, self-assembly means something gets aggregated and builds itself. Now, suppose you have a house, yeah, and you have to build a house. Then what do you have? You have constituents. You have bricks, iron rods, sheets, I don't know, cement, stones, and they all have to come together in a certain way to build the foundation, the rooms of a certain size, and there is a roof, and there might be another layer on the top of it. And how does it happen? It is made by engineers and masons, and I don't know, yeah, people putting together bricks and so on. Yeah, that you can completely relate to it. Now, the holy grail of self assembly and self organization is But suppose you have molecules, just like while building a house, you had bricks and rods and cement and I don't know what else. Then suppose you have molecules. Now you tune the effective interaction between molecules, and as they undergo Brownian motion, random motion, they would come close together, orient itself in the particular direction, and when they orient themselves in the particular direction, they would simply stick together because of a free energy minimum or energy surface. I mean, it's a free energy if it's thermal, and it will build a large structure. So what you are playing with is tuning the effective interaction between molecules, use entropy, random forces, and I'll explain that also. And it will it will automatically build itself a house, not a real house, but here I mean a big scaffold of molecular structures. Okay, so here I used a lot of terms. So that is the holy grail. That's the self-assembly. And if it is driven by external forces, you call that self-organization, non-equilibrium, statistical physics or thermodynamics if somebody is comfortable with it. So, here one of the most key important points is Brownian motion. Now, many of you would have heard of Brownian motion, but what I'll do is show you some pictures and videos because you might have heard it, but you don't visualize it. So let me try to do that. Uh, so let me share my screen. So is it visible?
Yes, sir, it's visible.
Yeah, so here what you have is extremely small, tiny specks of particles, colloidal particles. It's from YouTube. You see that I've just searched Brownian motion of colloids. And if I play the video, you will see that there are extremely small particles. They're randomly moving inside the fluid, inside the background water. And the reason they are moving and they also can rotate, take different orientations. Now you can see it more properly. You see that they're just jiggling around in space, but over long time they're also going to move from one point to the other, and that's diffusion. They're also changing orientations with respect to each other, and that is Brownian motion. And so just because of the background fluid, particles are moving around. That won't happen with a cricket ball. But if you have very small particles in a background fluid, they're automatically changing positions and exploring orientations. Okay. Now, if you take just hard sphere, so usually you talk about crystals, right? And crystals form because there is an energy minima and so on. But even if you have hard spheres, completely hard spheres, where only if two spheres touch each other, they have infinite repulsion, else there's no interaction. And if you pack them well, so there is no energy minima. Okay, there's no potential energy minima. The potential energy is only infinity or zero if they don't touch. But if you increase the volume fraction, what is the volume fraction? The volume of the particles divided by the volume of the water or the container in which it is contained. So total volume by the volume of spheres. And you increase that to 0.0, 0.48 and 0.54, then in spite that there is no potential energy minima, it can get into a crystalline state. This is called hard sphere crystallization. This is typically things which are not taught even in the MSc. And the reason they become crystalline is not because they fall into an energy minima, but they go into a free energy minima by maximizing their entropy. If they're in a disordered state, randomly, they're randomly arranged, then each particle cannot vibrate around, it cannot move around its average position. If it's in a crystalline position, all the particles can move around and fluctuate about the mean position. This gives it more entropy, more number of microstates. The way it can rearrange themselves, it's not rearranging in terms of position. Each is moving around its average position in a crystalline state. but it can each can move around and explore more configurations, more microstates, more positions, and thereby, because to maximize their entropy, actually it goes from a disordered system to an ordered crystalline system. Yeah. So now this, in some sense, though this is called hard-sphere crystallization, it is using its random fluctuations, the kicks, the Brownian motion, the kicks due to the background fluid, to arrange themselves. Now this is an ordered state, right?
Sir,
So this is the simplest example. Yeah, yeah. Tell
sir,
me, tell me.
sir, I have one question. Like, if they are not ordered, like if they're disordered, then why can't they explore more number of configurations?
So basically, if it is so if it gets, yeah. So point is, then some of them will basically stick to each other. See, here they are perfectly ordered, each can move around in its position. But now suppose it was disordered, some place it will be more packed, and at some places there will be more space, right? Where the particles can move around more freely, but at some other place in some random configuration, particles might get more packed. In that case, the ones which are getting packed, they can't move around much. Some particles can move around a lot. And if you do your calculation and free energy minimization, you will see that this has the lowest free energy.
Okay,
If you don't
so
prepare this system experimentally carefully, it can get stuck in a random, yeah, so it can get stuck in a random configuration. But that is not the equilibrium. It is just like a supercooled well, it's not super cool. It's just like stuck in a local free energy minima. So if it is ordered, each particle can fluctuate around its average position. And thereby, each of them is contributing something to the number of microstates. Whereas if it is random, some will move around a lot, some will get stuck, some doesn't have enough phase space, means velocity and position space to move around. So basically, its entropy decreases.
got it, sir.
That this is happening. This is happening only if you go to a volume fraction. See, here volume fraction is important because the interaction is only infinity or zero. So here the control parameter. So usually in water we talk about temperature, changing temperature to take the ice to go to water to go to, I don't know, gas. But here we are changing phases by changing volume fraction, because the interaction potential is either zero or infinity. And this has been realized in experiments. This is not a theories construct or something like that. Just wanted to clarify. Yeah. So sorry. Yeah. So that's what. Uh, so this is the simplest example of getting ordered by entropy, getting ordered to uh, getting ordered to maximize its entropy. So this catchword was created, ordered by entropy. There are other examples of self-assembly and self-organization as well, in case you want to know something about it. But I think I've spoken for a long time, so I'll just hand it over back to you.
Thank you so much for the answer,
Hello.
sir. And it was a very very great example which you gave. So my next question would be about specifically about polymers. Since I remember in your talk that you gave in your college, you talked a lot about polymers, and also, so what are polymers, and can polymers also organize themselves using entropy or something? If you could say something about polymers.
Yeah, they do. Um, okay. Uh, okay, so polymers. See, we all get introduced to polymers in our class 12, where we basically say that polymer is a self-repeating unit, and that creates long chains of molecules, and you can have. So it's typically taught in chemistry. But physicists also study polymers, and the physicist perspective is quite different from that of chemistry. So the polymer chemistry actually helps you to make, very useful objects, and we use polymeric materials all around um, uh, our daily life. But the physicist's perspective is not to look at these chemical constituents, but they look at polymers as an objects with multiple degrees of freedom. Actually, so usually when you talk about gas molecules, so gas molecules typically have, I mean, the degrees of freedom are position px, like momentum XYZ and position XYZ. Whereas here I'm showing you a video of a polymer. It's made by one of my students, and here I'm making a polymer. There are 100 beads. They're just spheres connected by springs. You cannot see the springs because I have not shown them. But what you essentially have is spheres connected by springs, and it is suspended in a background of water. I mean, no, this is a computer simulation. So the effect of the water or the Brownian kicks is taken by the Lajva equation, in case you know what it is. And so here I'm not very worried about what are the chemical constituents, but any long chain molecule given a suitable length longer than so-called persistence length will behave in the same way. So physicists are interested in the universal properties of long chain molecule, and in particular they are interested to look at entropic effects of polymers rather than trying to fine tune the chemical constituent to make something useful. I mean, we can also guide the chemical engineers, but we can't really fine tune the chemistry. So here what you see is a 100 monomer polymer connected by springs which you can't see and a background fluid. Each molecule is doing Brownian motion, but it is doing Brownian motion subject to the constraint that it is connected to its next neighbor by springs. As a consequence, each particle wants to move a random motion, but it is held back. As a consequence of this, you see, if you saw right from the beginning, that this entire polymer is constantly taking different conformations. So there is one polymer, it not only is having different positions, velocities corresponding to a particle, which is the center of mass motion, it is also has a large number of conformations, and these conformations essentially contribute to different microstates if you have done your statistical physics. And this means that this one single object has a, of course made up of constituents, has a large amount of entropy. So when you're studying polymers, you're really looking at consequences of entropy, reorganization due to entropy, entropic forces. Now, this entropic forces is a term which you typically don't get to hear. So that's why I have a particular video to give an idea. Well, here essentially what you have is four polymers connected, I mean, colored differently, and all that you see that each of these polymers are again taking different conformations. So you have a pink, yellow, blue. So there are four linear chains, and they are all changing conformations. And just note that on an average, if you let them equilibrate, they'll have an average size. And this is important in what I want to show you next. So I was talking about entropic forces. And is this the video? Rubber? Yeah. So let me show you this. This is a very interesting video. Now, let me stop this first. Now, so see, in your college you study about steel and metal, and I think you might guess that if you heat metal, aluminum, steel, etc., or iron, then as you heat it, its elastic moduli will actually weaken, which means it will go down. Means you can pull the metal rod more easily. On the other hand, if you heat a rubber band, okay, so there's a rubber band and there's some weight has been now watch here carefully. The rubber is being heated and the distance is increasing. Means this is becoming It's basically contracting essentially. See, this is the large distance. It means that this young modulus has become higher, or whatever elastic moduli before it got burned. Just to repeat, see, you had some metal. This was stretched. This was stretched. Yeah, this is under stretch. Now, if you heat it for the same amount of load, this is this distance is increasing. It's contracting. The rubber is contracting. I mean, yeah, the stretched rubber is contracting, which means the Young's modulus has gone higher. And this is a consequence of entropic. Here, the potential energy is not so much acting, but if you are stretching a polymer, the number of conformations it can take is less. So when you heat it, the U minus TS, the free energy, the TS is dominating more. And yeah, I mean, it wants to explore more conformations at higher temperatures. And because it's stretched it, there are fewer number of conformations. And so this is an example of entropic force. I mean, beyond that, it will take me a bit more to explain. So this is basically what I mean by polymers and polymer physics and how you can play with entropy. Just one more example. I find this very interesting. Just yeah. Now, so this is also done made by my student. Okay, suppose you have gas molecules, one colored red and one colored blue, and they're put in a cylinder. Why cylinder? Because we model bacteria, bacterial chromosomes, and so on and so forth. Now, you know that if you have demixed, on one side you had red molecules and you had the other side you had blue molecules, maybe oxygen and hydrogen. Though here we don't have the details, we just have hot spheres doing Lagrange motion. And if you basically mix them, Lagrange if you do, you see they get mixed, and they mix, but get mixed to maximize their entropy. Yeah, if they're mixed, the number of microstates each particle can access is more. On the other hand, if you have polymers under high confinement, so it's the same size, is the same size of the cylinder, the same number of same number of red spheres and blue spheres, but they are connected by springs. And if they are initially mixed, they will spontaneously demix. One side you have got the blue chain, other side you have got the red chain. Just to look at it again, initially it was mixed, but because of entropy reasons, they demix. And this is completely opposite to what you saw for gas molecules, where they actually mixed. And this is what is taught in your the gas molecules will mix to maximize their entropy. So just the chain connectivity is making the polymer behave in a completely different way. Now, why does that happen? That will take me some time to explain. But just by modulating entropy or connectivity, or here basically, yeah, I mean, because it's conformational entropy essentially. The confinement of the cylinder is extremely important, just to emphasize. You can get very strange, weird properties. And in fact, it is this property that we use. So this was discovered around in 2006, and but this is the basic property that we use to study chromosome physics and so on and so forth. Yeah, but I gave a very long answer. So I'll
Thank you,
just
sir. That was a very, again, a very beautiful answer. And I got this idea like how we can use some physics principles like free energy and entropy to study a wide range of phenomena which appear very like different at first glance. So my next question would be, so if we go to even more complex systems like DNA, chromosomes, and life itself, because DNA and they are the basic building blocks of life. So what does physics have to say about that? Like the physics of life has to say about that DNAs and chromosomes, and in your experience, in your work.
we see chromosomes are being studied since a very long time. I mean, So DNA double helix was discovered, I don't know, 53, 54, by Watson and Crick, right? And people have been studying various aspects of DNA for a very long time. But that has been more at the very microscopic approach. I mean, just to tell you, so the broad, what is the broad question? How does DNA work? Because DNA contains, it's a very long molecule, and how does it work? Just to give you an idea, let me share my screen again. So usually the DNA that you talk about uh, is this double helix, which is 2 nanometers long, and each helix turn has 3.2 is around 3.2 nanometers. Yeah. So this is what has been studied, and even histors. I'll come to this because this relates to DNA organization. So this is as what has been studied, where the chemistry, biology, everything is important. I cannot, with my statistical physics principles, study DNA at this DNA double helix, because there the chemistry is important. I look at it at a much larger scale, where I can use statistical physics for physics of flexible molecules to look at it. Just to make it clear, see, typically you correlate the word chromosome with such X-shaped structures. Okay, so what are these X-shaped structures called the chromosome, and what is the DNA? So the DNA is this double helix. They are made up of these bases A, T, C, G. But just to give you an idea, in the bacteria, inside a 2.5 micron cell, okay, um, of length, you have 2 millimeters of DNA coiled inside. DNA is a highly charged molecule. Okay, and for a human, let's talk of human. So inside the nucleus, so here, so because bacteria and human cells are very different. Bacterial cells do not have a nucleus. Human cells do have a nucleus. So suppose nucleus, yeah, I hope you know what is a nucleus. No, but cellular nucleus, not atomic nucleus, please. So this is a nucleus, and that's for a typical human cell or a eukaryotic cell is around 10 microns long. I mean, in diameter, or diameter or radius of what I'm sure, but is that's the order. And inside 2 meters of chromosome DNA, if stretched end to end, is packed inside the nucleus. And that's just to give you an idea. If you, because microns is very difficult. I mean, for me it is very easy, but microns is something which people might not relate it. So if you multiply 10 microns by 10 to the power 6, you essentially get a 10-meter object. It's like a truck. Truck is approximately, I think, 10 meters, a very large truck. Okay? And inside that, 2 meters of DNA is coiled and packed inside, and it's highly charged. So what is 2 meters? So if you are scaling up your nucleus by 10 to the power 6, 2 into to get a 10-meter. Did I do that right? Yeah, 10 into 10 to the power minus 6 into 10 to the power 6 is 10 meters, right? Then even this 2 meters, you should multiply it by 10 to the power 6 to get a proportional of scale. And then your 2-meter DNA would become 2 into 10 to the power 6 meters, which is essentially 2000 kilometers. Did I get that right? Yeah, I got that right. 1000, yeah. So 2000 kilometers of wire, thin wire, is packed inside. So what is 2000 kilometers? It's almost the length of India. India from Kashmir to Kanyakumari is around 3500 kilometers. So that amount of wire, if suppose you are packing inside a 10-meter truck, but it is not just random packing. They have to arrange itself in a certain way because they have to do their work. Their work includes transcription of genes, getting replicated, one cell becoming two cell. For that, the DNA needs to be replicated. And for that, there is a very hierarchical organization. Again, the word self-assembly and self-organization comes. So what you have is this two. So so that was just to give you a scale, because you can't imagine microns. I just multiplied both 10 microns by 10 to the power 6 and 2 meters by 10 to the power 6. So basically 2000 kilometers of thin wire has to be packed inside a 10 meter truck. But in reality, what you have is this 2 meters. And this is highly charged. And to pack so much charge inside a small volume is very difficult. It will simply blow up. So what happens is that this DNA is wrapped around some proteins which are positively charged to form something called histones. So these proteins, positively charged proteins, are called histones, and they are wrapped around to form something called a nucleosome. So this was 2 nanometers, and that's wrapped around histone to form a 10 nanometer nucleosome. Now these nucleosomes, these are now your building blocks. These building blocks also organize themselves into some zigzag type of structure, and this is also being studied by phases. So what is the shape of the zigzag structure? How how stable is it? How can it change, and so on and so forth. Now this zigzag structure, if you look at this scale, itself is like a wire. So this was like a wire, 2 nanometer, and then it became something like a 10 nanometer thing. And these arrange themselves into some zigzag wire, which might be around 30 to 50 nanometers in width, and it goes on in length. Now, this, if you now zoom out further, is essentially like a thicker wire. And how this organizes itself at the large scale is what is not known at all. Now, usually it is these wires are more of basically these are different chromosomes of eukaryotes. This blue, green, this is how it is usually. It's spread out. But only during cell division do they pack further and get into this X, X-shaped object. That is during only cell division. That is called the traditional chromosome. But the physicists basically, even if they are spread out like this, so basically any higher order organization beyond this length scale, we call it the chromosome. And how they organize and keep changing their organization to activate different genes, do transcription. These are the questions that I'm interested in. I'm actually at the moment I've not looked at eukaryotic cells. Eukaryotic cells are cells which have nucleus. I'm just entering the area. Like a true physicist, I've been always wanting to start with simpler systems. See, even when you do your quantum mechanics, right? You first do pre-particle, and then particle in a box, and then the hydrogen atom, and only then do you go to sodium, iron, and more complicated systems, right? So the same principle here. I'm at the moment I am not looking at eukaryotic cells. I'm looking more like bacterial cells. Why? Because they have only one chromosome. That's much simpler than looking at 46 chromosomes. I would know how to do the physics of it. So at the moment, I'm looking at bacterial chromosomes, which just have one thing, and and bacterial chromosomes are also simpler in the sense they don't have the so-called mitotic spindles, which basically segregate chromosomes once they are made a copy of itself. So this happens only in eukaryotic chromosomes. And in bacterial cell, they don't have this complex machinery. In fact, the principle which I showed you, this so a big question has been that if they don't have these mitotic spindle proteins which pull the chromosomes apart once they have been replicated means they made a copy of itself. How does segregation inside the bacterial cell happen? Broad questions. Segregation of replicated bacteria, right? And it was not known till 2006. Even now today it's not known. But in 2006, it was proposed that the same entropic mechanism which I showed you a movie of, this one. Yeah. So two ring polymers basically segregate into and due to entropic reason. The same mechanism was proposed by somebody to explain. Where did it go? Yeah, to explain, saying that maybe that is a mechanism. Entropic segregation is a mechanism of chromosome segregation. Once a mother chromosome has been replicated into two daughter chromosomes. In fact, that's how I got into these ring polymers and etc. And this principle, right now, I mean, when it was proposed, it created a lot of controversy. But right now, in any review paper, you will find that, well, entropic segregation of chromosomes only in bacteria. This is not for eukaryotic cells. Might not be the whole story. I mean, entropic segregation of chromosomes in bacterial cells might not be the whole story, but it is definitely an important ingredient into this chromosome segregation picture. And my work is actually beyond this. Yeah. Sorry, again, I gave an extremely very long answer.
No, I mean,
But,
it's
unless I spend some time explaining these, just throwing jargons actually doesn't
absolutely,
help, I think.
it's not possible to
So,
give a feel of these kind of topics by keeping the answer very short. So that was a very interesting answer, and that brings me to my next question. So uh, like again I said about the complexity of life. So as a physicist or in general, how do we distinguish living matter with non-living matter? Like, is there any clear line of distinction, or is it still somewhat vague or somewhat gray? Like, how do we define living matter and non-living matter?
that's a research question. Nobody knows. What we see, physicists have been playing with self assembly and self organization for a long time. I mean, that's what I had been doing. Now, those principles we are saying, can we put it together and take it forward? Because the human system seems also, I mean, by human, I don't mean human, by humans are too complicated to study. We have, I mean, even simplest, dumbest bacterial living matter, there's a lot of self assembly and self organization. Molecules come together, there's the nuclear, there's the cell membrane. By the way, people have been studying self membrane. For quite a long time, actually. Yeah, but that's all in isolation. Somebody is looking only at the cell membrane. Somebody is looking only at the proteins. Somebody is looking only so somebody has been looking at protein structures. But here now, in physics of life, that's different from biophysics. So in biophysics, you are basically looking at individual properties of molecules using tools which were present in physics, like X-ray crystallography, NMR, and so on and so forth. Those are physics tools. But now is the time, because of various advancements of theory and because we have been playing with self-assembly and self-organization, can is the time where we are saying how do different molecules come together to build a something called the living cell. So that type of research has just started. I mean, it was there even in the 1980s, but in a major way has started only 5-10 years ago. I myself heard the word physics of life, as I told you, 4-5 years ago. And I mean, I saw that people had started working on biology. I regularly go to international conferences, and I was initially surprised. Ye kya ho raha hai? Did I realize the same things that we are learning about self-assembly, self-organization? No, we were looking at it in bits and parts. We still are looking at it in bits and parts. But now is the time to ask questions that how can we integrate all these different little domains of knowledge? How do they come together and build a living cell? Simplest, dumbest living cell, bacterial cell. We have no clue. So at the moment, the answer is I don't know. Nobody knows in the world. But at least we can do controlled experiments. We have know how to. I'll tell you how a cell membrane works. Now we can put some molecules or proteins or some chromosome inside it and pull it, pressurize it, and now we have experimental techniques. Physics has to develop first to be able to pull molecules. See, the same molecules, the same thing. This, you can hang weight. So spring balance. Now you are again doing a spring balance, except you are pulling molecules. There you are pulling rubber band. That's a macroscopic object. No, but the technique, AFM, atomic force microscopy, various spectroscopy techniques, different microscopes to go beyond the diffraction limit, they had to be developed. Unless they are developed, how can you ask this question? You can pontificate whatever you want. But unless your theory is validated by experiments, you check, okay, my theory, this is what I propose, and it is not working out. Let me modify it and then see whether it matches with experiments. So unless, else you give 1,000 theories, who is preventing you? Right? That's philosophy. You give whatever theory, it is sitting in some corner. That's what, unfortunately, physics has been for some time. Some experimentalists will validate, but that's not how soft matter works. Or physics of life. If you're giving a theory, you try to say, this is how we can test it. And then so that this physicist, experimentalist, chemist, biologist, they all come together. There's no theory, experiment, computation. They all come together. See, this is what we are proposing. Can it be validated? If it's not validated, throw it away. Give a better mechanism. So all this is happening, and this is currently going on actually. And I don't know. Sometime we will get to know. At the moment, we don't know. But various techniques have improved, experiments have improved, and that is the reason we even dare to ask physics of life questions, because previously we are happy doing, because we don't even understand self-assembly and self-organization in simpler systems. Those are the things which we were playing with various kinds of polymers and dead molecules, amphiphilic molecules. Just to give you an example, cell membrane, how does it work? We actually know that for some time. Where did it go? Yeah. So people have been playing with self-assembly, self-organization for quite some time now. If you have a molecule which has a large head represented by this blue point, and it's water loving.
Sir, are you screen sharing? Because I cannot see your screen.
Oh, I didn't screen share, is it? Yeah. Oh, sorry.
Yeah, it's visible now.
Yeah. Now suppose you have an amphiphilic molecule. What is an amphiphilic molecule? It's a water-loving head. Suppose this part is a head, and it has some chemical structure. Of course, the chemical structure is important if you want to tune the perfect properties. It's to chemist. The physicist will say, "Oh, we have a water-loving head. It attracts water with this much energy and a water-hating tail." Now, just by changing the shape or the relative size of head and tail, so what would the tail do? The tail does not like water. It wants to stay away from water. The head wants to face water. And if you throw a lot of molecules inside water, what will they do? And you keep increasing the concentration. So at very dilute concentration, they all will be spread. But if you keep increasing the concentration, the tails will aggregate together and shield themselves. Okay? And the water-loving head will basically be on the outside, and they will form small spheres. So this is self-assembly. Now, if you have a smaller ratio, more of an equal ratio of the head and tail, where this part doesn't want to face the water. It wants to face the water, and this doesn't want to. Then they can form layered structure like this. They can form certain lamellae. Well, here I think you don't even need water. All that you need is basically, okay, here you have a polymer. Here you have a polymer. Now, this is the wrong picture, I think. Anyway, here what you have is a polymer, which is blue part and a red part, and the red part doesn't want to be in contact with the blue part. And then you will find, so because it doesn't want to be in contact, and if you put enough of these materials inside it, what you will have is essentially they will form these layers. The blue ones will form layers. So if the large number of molecules, they will form a layer, and the red molecules will come together and form a layer, and that's how they minimize contact with each other. But if we change the shape, they can get into cylinders, they can get, so inside this there would be all these molecules which will pack inside. And here I think what you have is, yeah, uh, well, depending upon changing the length of the molecule, you can get these spheres and cylinders. It's all a matter of which doesn't so which molecule doesn't want to see. So basically, if you change the length, there is a smaller length of a molecule, right? So most of it will be blue. So it will basically rearrange themselves to form all these different self-assembled structures. Yeah. And I think there's a separate figure. Yes, this is the one for surfactant. Well, this is also for diblock copolymer. So basically, what I'm saying is by changing this effective interaction between head and tail, or in this case, the length of one part of the polymer chain. This is called a diblock copolymer. There are two blocks, A and B. A has one type of interaction, B has another kind of interaction. You can get all these very different self-assembled structures and shapes at a larger length scale. Now, this itself is pretty complicated. Now, how this and many other objects inside the living cell will come close together and form the living cell, we at least don't know at this moment, but this is the time to try to figure it out. That's all that I can say.
Okay,
But
thank you,
I
sir.
couldn't answer that.
That's
Yeah.
okay. So now finally I would like to ask a different kind of question, like not anything technical, but like usually physics is a subject which is at the high school level people usually fear physics or find it difficult and boring. And I think that has got a lot to do with the way it is taught, because even I didn't used to like love physics when I was in school. So what do you think the way physics should be taught, especially to the young generation, not to the like the university students, and also in general, how do you think we can improve the way physics is taught, and what would be your suggestions to somebody who wants to pursue a career in the physics of life, do research in physics of life or something, because you yourself have explored this area a lot, and the good part is
I have just started exploring.
yeah, that's what I'm saying.
I've
But
just started.
so you are even a better person to say, because you have started exploring and you are aware of the this is a new field. So you can tell, you can advise somebody who wants to transition into this field maybe. So because the feeling I get is this is where the future of physics lies, not in the conventional theoretical part. So a lot of people should take up this line
No,
of
no,
research.
those also have a lot of scope. Condensed matter, plasma, light,
Yeah.
nanostructures, they also have
So
a
they have a
scope.
scope, but I was talking
Also
about
trying.
but stuff like string theory and all. I think they don't have a lot of scope. So
Oh, that's not, I don't even know whether that's physics. They keep
exactly,
on writing theories. There's no validation. Why should physics is a study of nature, right? Where is nature there? You
absolutely.
can theorize. See, going from Newtonian 1 meter to 10 to the minus 6 meters, you have Brownian motion. Going from 10 to the minus 6 meters to 10 to the minus 10 quantum mechanics. There they have extrapolation of 10 to the power, I don't know how many times. I don't really know. And they say somebody will someday validate it. And you keep on writing theories.
Exactly. So
I have no comments about it. I
that
think it's very weird way
that's
to
that's
do
what I'm
physics.
that's what I'm saying. Like that is not really physics, and I think the future of physics lies in this
I
kind of
don't know whether it's physics or not. That's you're going into controversial domain. I
yeah. I mean,
think you'll be slaughtered.
I mean, so that's what I'm
You
saying.
might
Like,
end up getting slaughtered.
what would be your advice to somebody who wants to study physics of do research in physics of life, and also some suggestions about how to better teach physics, because this is something I think is very important in our education system. It's very lacking. So
I think better teach people can't relate to physics because they see a lot of equations, they can't relate it to real life. So if you put in more experiments where whatever is being taught, uska ek realization dekho. This is electromagnetic force. Okay, people have played with magnets, agreed. But after that, you keep on teaching this and that. So many people can't relate what they're seeing around themselves, the experiences, to what is being taught. If there are more experiments, if there's more contact with nature, along equations are important. I'm not saying equations are not important. But kitna information loge in equation basically summarizes a huge number of experiments in one small simple things. But at the same time, that equation has to be also connected with real life. If you can give more pictures, if you don't have experimental facilities, today there's YouTube. You can see so many experiments in YouTube. I had never seen Brownian motion. I had only read about Brownian motion, but there's a random motion. But here I said, no, no, no. Dekhta hai. How does it look under the microscope? I didn't bring you a microscope to discuss, but at least I showed you कि ऐसा होता है. This is what happens, right? So if you don't have, at least you have YouTube, internet connection, then you can build a. So this is I myself don't know. I'm learning. Then we what I did is we're told Maxwell Boltzmann velocity of distribution. We all know how to derive it. I also derived it. But while I was teaching, I said, why should I believe it? Okay, who knows the maths is correct or not? And then I realized this Maxwell Boltzmann distribution was proposed by Boltzmann. I don't know who exactly proposed it, but like late 1800s, I would guess. Boltzmann himself might have done it in all probability. But experimental validation was 1927 after quantum mechanics. So how gas molecules move and that their velocity distribution is this. And it's a very simple and elegant experiment. But we don't put this, we have derived it, assume the assumptions, believe it, and reproduce it. Now, why should we believe those assumptions? We don't discuss how can it was this validated. The problem is we also have this. You have to teach a large amount of physics in 5 years, but where is the reality? Derivation to karte gaye. How do I know whether it's true or not? Why can't we ask the question? We said this has been discovered. It's truth. How was it validated? We don't discuss about validation. We don't discuss about connection with nature. I think that's a problem. See, I read about critical phenomena and a lot, but only after YouTube came, I said, "Daddy, critical phenomena suna to hai." Read a lot of derivations. Let me see how it looks. There are fantastic videos on whatever critical phenomena be. Just YouTube it because I can't go on talking about it. Uh, I saw it and it was great. And I show everybody in class कि देखो इसके बारे में तुम पढ़ते हो, but this is how it looks in reality. And I myself, I didn't have the chance. I just read, this is what happens if something goes milky. If you go near the critical point, there are all these strange properties. Looking at it gives a completely different dimension. That's at the MSc, BSc level. I'm sure that is the problem even at the lower level. तो थोड़ा connect होना चाहिए ना. Physics after all is a study of nature, and nature ही नहीं है. So what would you do? I don't know. Physics of life, it has a lot of interesting stuff happening. So much weird phenomena which is there to explain. People go searching for problems. Now problem, questions after question. Why does this happen? Why does that happen? From the physics perspective, there's the biology perspective and the physics perspective. How do you get this phenomena? Why does shape happen? Why does leaf have this shape? Why do you have shape? How are shape of leaves decided? What is the shape of organs decided? What is the shape of cells decided? So much. I mean, quantitatively. I mean, you might say that we don't know. That's perfectly okay. But at least we are having tools to do these experiments. And so I think there's a lot of scope. And I mean, you can see the amount of funding out of students. In India, people don't know about physics of life. But outside India, I mean, it's big. It's big. Like from soft matter, there are already We have soft matter conferences. Previously, within StatMech, of course, StatMech, but I'm talking of the soft matter because as complex fluids, as many sessions are already there. Any conference, and that just happened in the last 6, 7, 8 years. Just started as a trickle around 2014 when I was very surprised. 14, 15, 16. What happened? Where did life come in physics? And now there are multiple sessions. And I get advertisements of PhD advertisements which are advertising the world. 90% of soft matter, not StatMech. Sub branch of StatMech is soft matter. Within that those are the people going into physics of life. Many others are also. This statement is not accurate, but the sake of brevity, I'll just keep it at that. There's a lot of funding from engineers, partial differential, depending upon what phenomena you're looking at what scale, you have different methods, you have different tools that people are doing. And physicists and biologists are working a lot together. Not in India, but in India, it has just started. You might know that NCBS has a special physics of life program. ICTS has a special physics of life program. It started, but outside India, it started in a big way 10 years ago. So
So
there's a lot of scope. And here, experiment, computation, theory goes hand in hand. You can't just bluff.
yes, thank you, sir. Now, so I would like to
Right.
end. I would like to end the discussion by saying that first of all, sir's motivation and his passion for the subject. I think that is really like almost infectious. The way he speaks. I mean, not just in this video. I attended his talk in my college, so I can tell that it's really very infectious, and he has this rare ability to like kind of grow your interest in this subject. Because if I just speak one or two sentences about myself, I was initially interested in the quantum foundations and all those, like studying the theoretical formulations of quantum mechanics. Even my undergraduate dissertation is on the path integral formulation. But then I slowly, after listening to Sir's talk and after doing a bit of YouTube study and stuff, like yeah, as Sir said, YouTube is very important because today we have the resources to study visually and connect with nature. Like we should not, as physicists, we have a responsibility of describing the real world around us, not just talk with our equations, but talk with the world around us, as Sir said. And that can only be done through experiments and
Also do experiments. Also,
yeah,
please
yeah,
do experiments. I'm sorry to interject,
yeah.
but just YouTube nahi देखना है. We should actually play around, pull, push, pass electric shock. Sorry, but I had to interject here
No,
because in
absolutely.
Calcutta the importance of experiments is yeah a bit less. Everybody wants to be a theoretical physicist. What is a physics without experiments? So I had to interject. I'm extremely sorry
No, no,
for
it's
that.
I get it, and I have studied undergraduate in Kolkata, in Calcutta, so I know this what sir is telling. I have faced this in my college also. People are either into theory, or a large percentage of people are into astrophysics. But this understanding the complex physics of complex systems, physics of life, or even StatMech, very, at least in my class, there are very few, I could say, who are really into this. So but the thing that I was telling is like recently, that's why I shifted to this. And sir told about a lot of development even in India, like some programs in ICTS. And I recently went to IIMSc Chennai Institute of Mathematical Sciences. They have a separate department of computational biology, which I think is very rare in India. Like whole,
Very rare.
yeah.
Mathematical sciences, computation, biology. Absolutely. Many of them are my friends, Rahul and Sitabro, and yeah, yeah.
I did a project under Sitabra sir also, and there also we explored like synchronized oscillations, and this might have applications in cardiac modeling as well. So it was
Beautiful.
the best part is it's a fusion of theory, mathematical modeling, computation, and experiment. It feels like you're actually doing something, not just like mindless equations and stuff. So this transition, which I think Sir's story can serve as a motivation for all of us who wants to go into physics of life, because Sir himself was initially into StatMech and all. Like physics of life is new to him, but in only a few years, the way he has caught on and the way he finds it interesting, I think we can learn from him. All of us who wants to explore physics of life, I think he can serve as a very powerful motivation, for a very powerful example for us.
Not have biases, stupid biases like me. I was biased, but I broke my bias, thankfully.
Yeah, I
I
mean,
could.
all humans have biases. That is, I mean, we have to breaking the biases where we can, like, that is what we can do. Biases, I think all of us have biases. So that's what I with that I would like to finish the discussion, and I really hope you enjoyed the discussion, although it's a bit long, but we discussed the stuff, sir discussed the stuff in very rigorous manner with showing illustration and examples, and I think that's more important than just discussing without screen sharing and showing stuff. So I think that that the
Yeah.
that I think that made all the difference. So let me know in the comments if you have any questions, or whether you enjoyed the video. And once again, thank you so much, sir, for your time. We're really honored
Thank
to
you
have
so
you.
much. I'm sorry I took too long, but it's
No, no,
okay.
it's the only way.
Thank
It's
you for
the
inviting me. I hope I arouse interest in some students. That's the reason yeah,
Absolutely.
I want to reach out to students. I like to talk to students, and I want to tell students because this is some information about physics of life which is not available to Indian students easily.
Yes.
Thank you
And
very much.
yeah.
Okay, so we'll end the meeting here. Yeah.
Yeah, and one last thing is, thank you for watching. One last thing is, I will also add some links in the description of some relevant SIR's webpage, and also some relevant materials regarding the physics of life and StatMech. So if you are interested, those of you are interested, they can also check it out. So thanks for watching once again. Thank you.